The universe is a vast dynamic place, and its expansion is one of the most profound discoveries of modern science. In 1929, astronomer Edwin Hubble made a groundbreaking observation. Distant galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. This led to the understanding that the universe itself is expanding, not just the objects within it. This concept dramatically changed our perception of the cosmos and laid the foundation for the Big Bang theory. It also implied that the universe had a beginning, a moment in time when everything as we know it started from a single, extremely dense point, in addition to uncovering the large-scale structure of the universe. Scientists have also delved into the very materials from which we are made. Throughout the 20th century, particularly around the 1950s, research began to reveal that the elements found in our bodies, carbon, nitrogen, oxygen, and others, originated in the nuclear furnaces of ancient stars. These elements were formed through a process called nucleosynthesis, which occurs when stars fuse lighter atoms into heavier ones under extreme pressure and temperature in their cores. When these stars reached the end of their life cycles and exploded as supernova, they scattered these enriched elements across space. Over billions of years, this material coalesced into new stars, planets, and eventually life, demonstrating that our bodies are quite literally made of stardust. By 1957, scientists were not only studying the composition of stars, but also recognizing the powerful forces at work in the cosmos. The night sky, once seen merely as a source of aesthetic wonder, became a window into the energetic and often violent processes that shape galaxies and stars. The universe, while beautiful and serene from our earthly perspective, is far from quiet. It is a place of constant motion, collision, birth, and destruction. Much of what occurs across the cosmos remains unknown to us, despite centuries of observation. We continue to ponder existential questions. Why are we here? To the formation of the planets and stars, could things have turned out differently? These questions fuel the field of cosmology and push us to keep exploring. Yet, in our daily lives, we often ignore problems until they become too large to overlook. This tendency is mirrored in our approach to astronomical phenomena. One striking example is Betelgeuse, a massive, red supergiant star located in the constellation Orion. Betelgeuse has recently drawn attention because of unusual activity that could suggest it's nearing the end of its life. Observations have shown that the star is shaking and trembling, signs of internal instability. Such behavior has alarmed astronomers as it may be a precursor to a supernova explosion. Betelgeuse is enormous. Placed at the center of our solar system, it would extend beyond the orbit of Jupiter. Its immense size and variability make it a subject of ongoing scientific interest. Betelgeuse is not like ordinary stars. It's classified as a red supergiant. It is in a late stage of stellar evolution. While it appears as a bright point of light in the night sky, it is actually located more than 640 light-years from Earth, in astronomical terms. This is a considerable distance. Even if we could travel at the speed of light, which is currently beyond our technological capabilities, it would take over 6 centuries to reach it. Using conventional propulsion methods, the journey would take millions of years. This gives a sense of the vast scale of the universe and the difficulty of interstellar travel. Despite its apparent calm from our vantage point, Betelgeuse is anything but quiet. It has long been known as a pulsating variable star, meaning its brightness changes in cycles. These cycles are caused by physical changes in the star's outer layers as it expands and contracts. The variations in brightness can be significant, ranging from a visual magnitude of 5 to nearly 0, a major shift that is visible even to the naked eye under dark skies. The pulsation cycles themselves vary in duration. Shortest is about 185 days, while the longest spans over 2,300 days. At times, these changes become unusually pronounced and deviate from the star's typical behavior. In early 2021, for example, astronomers recorded one of Betelgeuse's lowest brightness levels in recent memory. Its V-band magnitude dropped to 1.614, far dimmer than normal. This sudden dimming puzzled researchers and led to widespread speculation that Betelgeuse might soon explode. Further observations later suggested that a giant dust cloud expelled from the star had blocked some of its light. Still, the event underscored how dynamic and unpredictable massive stars can be. Betelgeuse's deep red color is due to its relatively low surface temperature, around 3,500 Kelvin. In contrast, the Sun, though smaller in size, has a hotter surface at about 5,500 Kelvin. Because Betelgeuse's temperature is lower, it emits less energy per square meter, which partially explains why it does not appear overwhelmingly bright despite its enormous size. Recently, Betelgeuse has shifted from a relatively stable state into one of increased volatility. This change is a natural result of its ongoing stellar evolution.
Yes.
Like all stars, Betelgeuse relies on nuclear fusion to sustain itself. In its core, hydrogen atoms fuse to form helium, releasing vast amounts of energy. However, in red supergiants, the hydrogen in the core becomes depleted over time. As the fusion rate drops, the core contracts under the force of gravity and the outer layers expand dramatically. Eventually, helium burning begins, producing heavier elements such as carbon and oxygen. But unlike hydrogen fusion, which is relatively steady, helium fusion is more erratic. This causes fluctuations in energy output, leading to instability in the star's outer structure. These erratic energy releases produce strong pulsations. As the outer layers expand and contract, the star's brightness changes, creating a cycle of light variations that can be measured from Earth. Along with this, the star produces powerful stellar wind streams of particles that strip away its outer layers. This mass loss significantly alters the star's internal structure and affects how it will eventually die. These winds are so forceful that they carry large amounts of gas and dust into space, contributing to the enrichment of the interstellar medium, the material from which future stars and planets will form. To investigate these processes, astronomers use a range of observational techniques. Photometry involves measuring the star's brightness over time, helping scientists track its pulsations. Betelgeuse's changes in brightness offer critical insights into its internal activity. Spectroscopy, on the other hand, analyzes the star's light at different wavelengths. This reveals information about the star's surface temperature, composition, and movement. As Betelgeuse pulsates, its spectral lines shift, allowing researchers to detect internal shifts and energy transfers within the star. In combination, these methods allow scientists to construct a comprehensive model of the star's behavior. By inputting data into powerful computer simulations, astrophysicists can recreate the conditions inside Betelgeuse. These simulations incorporate physics equations that describe nuclear fusion, gravity, and fluid motion, producing models that help predict future changes in the star's pulsation patterns. The aim is to link theoretical models with observational data, improving our understanding of how massive stars evolve and die. One of the most fascinating internal processes in Betelgeuse is stellar convection. In this process, hot plasma from the star's core rises toward the surface, while cooler material sinks back down. These convection currents transfer energy from the interior to the exterior, contributing to the star's brightness. As energy reaches the surface, it causes the outer layers to expand, and when the energy flow decreases, the layers contract. This rhythmic movement is what causes the periodic changes in the star's luminosity, making it appear to pulse like a beating heart. The interaction between convection and nuclear burning is complex and varies over time, adding layers of unpredictability to the star's behavior. These pulsations are not merely random fluctuations. They follow identifiable patterns and are typical of stars classified as variable stars. In the case of Betelgeuse, the cycles of brightness are tightly linked to the expansion and contraction of its outer layers. As the star expands, the surface becomes cooler and dimmer. During contraction, it becomes hotter and brighter. This balance is maintained by the competing forces of gravity pulling inward and radiation pressure pushing outward. When these forces fall out of equilibrium, the star's outer structure responds dynamically, leading to the variations we observe from Earth. As Betelgeuse approaches the end of its life, these processes intensify. The star is running out of fuel to sustain nuclear fusion. Eventually, it'll reach a critical point where it can no longer support its own mass. At that moment, the core will collapse, triggering a supernova, one of the most powerful explosions in the universe. This dramatic event will release an immense amount of energy, briefly outshining entire galaxies and sending newly formed elements into space. The supernova will mark the final chapter in Betelgeuse's life, leaving behind either a neutron star or a black hole. Depending on the remaining mass until that day arrives, Betelgeuse continues to offer astronomers an extraordinary opportunity to observe stellar evolution in real time, its pulsations caused by the interplay of nuclear fusion. Convection and gravitational dynamics serve as a natural laboratory for studying the life cycles of massive stars.